I saw someone running still, but we can start. Let me start yes as well. Yeah, let me start. Um, so thank you once more to the organizers. I think this has been an amazing school with so many pedagogical lectures. I've really enjoyed it, and I'm sorry that I have to miss tomorrow's final lectures, but fortunately I've seen that they will be uploaded. So anyhow, so my last lecture is going to have sort of quite a lot of overlap, I think, at least in terms of structures that you see with Sergei's previous lecture, and maybe even more with the things that he's going to talk about in the next lecture. But the physics is different. So 4 dimensions versus 3 dimensions. So what I'm going to do today, so this is my last lecture, and I'm going to combine a few of the ingredients that we've learned about in the previous 2 lectures. So first of all, that was the Seiberg-Witten geometry, so in particular this holomorphic section. In terms of the prepotential over our column branch. Second of all, we learned how 4-dimensional BPS states can be encoded in these geometric structures on a Riemann surface. And so maybe to remind you, these spectral networks, they were drawn on the UV curve. So this story is for a special case of n=2 theories of class S, even though I think many things can be generalized that I'm going to say. So maybe let's remind you and draw this picture of a particular spectral network. So generically, at least what Sergei called N, I call K. So generically for K is equal to 2, for Nash 2 theory, these spectral networks, we saw that they look like something like this. So there were 3 strands coming out of each of these branch points of the covering. And so we saw that we associate these spectral networks to a vacuum of the 4-dimensional theory and the choice of a phase. So those are the 2 parameters of my spectral networks. And so here I'm drawing a network at a generic point on the Coulomb branch and a generic phase theta. And generically, we talked about the fact that we can see these networks as being dual to triangulations. And we also talked about the fact that if you go to special phases, what happens is that these 2 trajectories, they will come together. The triangulation disappears, and there will be a saddle trajectory. And we talked about the fact that these saddle trajectories correspond to these 4-dimensional BPS states. Where the central charge is given by this theta. So maybe let's call it theta BPS, as I did before, I think. And maybe let's give it an index 4 dimensions as well, because these correspond to 4-dimensional BPS states. Right. So the final ingredient that I started talking about last time is that of these objects X gamma. And I told you that these objects, that they depend, so where gamma is an element of the electromagnetic lattice. And I told you that these elements depend on the isotope class, so the topology of the spectral network. So these are all valued in C star. And so what I want to convince you about is that these objects are incredibly rich and that they basically encode everything that you want to know about about the quantum cybercritin theory. So one of the things that I've already mentioned is that what happens, right, so we have this, so let's now look at these objects at a particular vacuum. So we look at a network which is specified at a particular vacuum of this 4-dimensional theory with a specific phase. And so the formula that I wrote down last time is that if we change this phase, so let's look again at this phase of the space of central charges. So I drew these as vectors in the plane. So suppose that we have this BPS ray. At a phase theta 4-dimensional BPS. And suppose that we try to determine what happens, and I'm going to tell you a little bit later about how you can do this, what happens to these objects S if you cross the BPS ray. Well, what happens is that you get this Kontsevich-Soibelman transformation. So I introduced 2 cycles last time. Let me do this again in this picture. So I introduced a 1 cycle gamma here, and I introduced a cycle which was dual. To this cycle gamma, in the sense that their intersection number is equal to 1. And then I said that what happens under such a flip of the network that corresponds to a BPS ray, well, what's going to happen is that this dual cycle, so the original one, the cycle gamma, is not going to, the object corresponding to that is not going to change, but this one is going to change. And it's going to change in the following way. And so in general, I wrote down that there might be, well, if I didn't choose this number to be 1, then I could write down this power, and as well I could write down this Donaldson-Thomas index omega gamma corresponding to this 4-dimensional BPS index. So in this case, because we look at a simple BPS state, just a hypermultiplet, this was equal to 1. Right. So I want to give you some intuition today about how to think about these objects and why they encode so much information. And so one thing I mentioned is that these objects are really coordinates. So these X, W, they form a local system of coordinates on a space that's very much related to this Coulomb, to the Coulomb range. So they are coordinates on, well, so I call this the Hitchin system in structure J, or in other words, the moduli space of flat connections on the surface C with coefficients in SL KC in general. And I started a little bit about telling you how we can find these coordinates from a perspective called W abelianization. So what I told you is that we have this covering, this ramified covering over C. And now we're going to go the inverse way. So suppose we start out with some flat connection. Valued in SLK. So what abelianization does is it tries to abelianize that flat connection into an abelian connection on the cover with respect to the choice of the topology of this spectral network. And so I want to explain in some more detail about how that happens. Well, you'll see. Or maybe just C star connection. On sigma. So I also told you that once we know how this method works, we can read off these coordinates. So we can just read off these coordinates as the holonomies over the cycle gamma of this abelianized flat connection. So that gives you a C star number. And so then it's clear as well, at least if you believe me that this map is sufficiently well defined. It's a one-to-one map in general with some additional data. Then it follows that these holonomies are coordinates indeed on this moduli space of flat SLK, C connections. So the idea is, so given that we have a spectral network that's maybe of this general form, generic form, so the idea is that we're going to look for a basis of sections such that the flat connection is diagonal in the patches which are complement to the spectral network. So this is a picture on C. So we have our flat connection. And what we're going to do is we're going to find sections, and I call these Si and Sj. We're going to find these sections such that the flat connection is diagonal. We know that we cannot do this across the whole Riemann surface, but we may do this in all of these patches. And maybe you remember as well that this spectral network, that it carried some labelings. So we introduced these labelings based on the fact whether this Seiberg-Witten form or the tautological 1 form, whether it was positive or negative when restricted to these trajectories. So we had to choose some trivialization of our covering. with respect to that, we can choose, we can choose a sheet 1 and a sheet 2 of our covering. And we can label these trajectories in such a way that either this contraction of lambda with the tangent vector is positive or negative. And so we find that these labelings are, for instance, this. Now it turns out that we can find a basis of diagonal sections such that if you cross a wall of type IK, well, this is not really maybe handy notation. So say you cross this wall of type 2, 1, you can find a basis such that this first element stays the same and the second element is different. So we'll see that in an example. And that means that across this trajectory, these basis elements, or the basis in these two regions, it will be related by a matrix which is of this type. So this is called a Stokes matrix. So it turns out that that you can always do this. You can, with respect to a spectral network, you can always find this basis on the complement of the network where it's diagonalized, and then the gauge transformations across these regions, they're given by these Stokes matrices. And so the non-zero element of this, so the off-diagonal element which is not equal to 0, it depends on the type of wall that we have. So if we would be looking at a 1-2 wall, that would be on the opposite side. Right. So I think it's, although I have to think about my time, I think it's maybe insightful to show how this works, how we get the coordinates that gives these wall crossing formula. So let me try to do this. So suppose that so this works for many kinds of topologies of spectral networks. What I will do here is I will show how this procedure works for generic networks which are dual to these triangulations. And so remember that the abelianization map, it depends on the topology of the network. So for each different topology of the network, I get a different set of coordinates. Right, so let me look at, and I'm going to draw it slightly different than the way that I drew this before, but it's essentially the same. So locally, in the case of a generic network, I can always draw the network like this, where these are some punctures on the Riemann surface. So I'll label these punctures. Because every trajectory from a generic network will eventually end in one of the punctures. Right. So I also told you that this abelianization map, it requires, it's not quite a map from the moduli space of flat connections on C to a map to the space of flat connections on sigma. It needs some additional data. I call this the framing data. And this is the data that you need to really make this map into a one-to-one mapping, so a bijective mapping from connections on sigma to connections on C. And this framing data, in this particular case, in networks that are generic, it consists of a line bundle, so in this case it corresponds to. So this is something different for any kind of different type of topology of network. But if the topology is like this, if it's dual to a triangulation, then the framing data you choose is as follows. So it's a choice of line bundle at each of the punctures. And so what you choose is you choose these line bundles to be invariant under the action of the flat connection. Well, maybe don't know how to. Well, let me just call it Cn, but it stands for any puncture. So, well, if I have a choice of invariant line bundle, that means that I can choose a section of that line bundle. So that means that at all of these punctures, I have an extra discrete data, which is a section SL which stays invariant under this connection. Sorry, what is this? SL, SK, and SL. Right, so what I'm going to do now is I'm going to construct the abelianization of my flat connection with respect to those choices. Right, and I also need to do that, I need to choose some labeling again and a trivialization of my curve. So let's choose it like this, 2, 1, 1, 2, 2, 1, 2, 1, 2, and 2. Right, so how am I going to choose my basis of section? So there's also, well, right, so these sections, they're defined near these punctures. And so if I want to compare them to each other, I have to parallel transport these sections to a common point. And so generically, if I parallel transport this section to the neighborhood of this puncture, then they will form linearly independent eigenspaces of the monodromy of this connection. That's a constraint on my connection, which I'm now imposing, and that means that these coordinates that I'm going to construct are really local coordinates on this moduli space of flat connections. A very mild constraint. But then I know that as a basis, this diagonal basis, say in this region, I could take SL, the vector SL, SM, because I know that they're linearly independent, and I know that my flat connection is diagonal with respect to these two sections. Similarly, I can do this everywhere. So I could do this here. And I do this in a way that when I cross a wall of type 1, 2, then my second element stays invariant. Whereas if I do this across a wall of type 2, 1, I leave the other element invariant. So this is going to be a bit fussy, maybe. But yeah, maybe this is an exercise to complete for yourself. So I can do this everywhere. So I can choose this basis. So you can work out yourself, I mean, how I choose this basis in terms of this framing of sections of the flat connection at each of these punctures. And right, so now the point is that I can lift this structure onto sigma, where I see the first component as the section of the abelian connection on the first sheet, and the second one I see as the abelian connection on the second sheet. And this works globally because these transition matrices are exactly of this Stokes matrix type. That is kind of a condition which tells you that I can actually glue this into a flat connection on sigma. Right. So then, once we've got this abelian connection, I could compute these spectral coordinates with respect to the spectral network. And so let me maybe give one example. So the example of the cycle gamma that I showed before, maybe in the interest of not having too much information in this picture, let me remove some of this. So let me choose my one cycle to be like this. So I know that this spectral coordinate is going to be defined as the holonomy of gamma of this abelianized flat connection. And I basically have all the information about this abelian connection because I know what the basis is at every point on sigma. And so you can compute what this holonomy is by computing what the parallel transport is of this abelian connection across a trajectory. So say a trajectory 1, 2. So suppose that I have a basis Si, Sj here. Maybe I choose it to 1. And I have another basis Si, Sk here, because I know that is the structure that I can always bring this flat connection in. So suppose I have a connection, have a structure like this. So can I answer what is going to happen to my section Sj when I cross that particular wall? And this is something that I can answer just by a few sort of elementary arguments. So first of all, this Sj, I've told you, it's something that lifts on the second sheet. It's a section of this abelian connection on the second sheet. And so if I parallel transport it to this other region, I'm not going to cross from sheet 1 to sheet 2. I'm staying on sheet 2. So it has to be something proportional to my section Sk. But the important information here is, of course, what is this lambda? What is this proportionality constant? And so since these sections, since they you can take their wedge product, and this gives 0 because obviously it's anti-symmetric. I can try to wedge this with the other element, Si. So I get that. Okay, let's call this Sj prime. So Sj prime is the parallel transported section, and I can express it as something in terms of Sk, a constant times Sk, and I'm working out what this constant is. So let me wedge all of these. So let me wedge the section Sj prime with Si. I get this formula, and so what I find is that my lambda is equal to Sj prime. Is that what I want? Let's see. So, okay. One second. Oh, yeah, right. So what I also know is, yeah, so sorry, there's one additional ingredient. What I also know is that since I'm talking about an SL2 bundle, I know that the volume form on my fibers stays invariant if I cross the trajectory. So I know that my Si wedge Sj is also equal to Si wedge Sj prime. And this is going to tell me then what my lambda is. So I'm using a couple of ingredients to do with the fact that I'm abelianizing an SL2 flat connection. And from that, I can derive what happens to the parallel transport of this section Sj if I cross a trajectory. Now, I can follow my cycle gamma, so I can start at any point, and I can follow it across these 4 trajectories, and I can see what happens across each of these crossings. And so this is maybe another exercise that will show you then that in this particular case that this x gamma can be expressed. So there's only 2 crossings which are non-trivial. So you have to, well, to do this properly, you have to choose on which sheet this gamma runs. So say it runs on sheet 1. Then I only find non-trivial crossings if I cross across this one and this one. Is that? Yeah. Well, actually, no. So there's 4 of them. Sorry. So there are 4 non-trivial crossings, but some of these factors they're going to cancel out. And so the result that you find is that this spectral coordinate, this holonomy of this abelianized connection, takes this sample form. So it's quite a simple computation in this case, and what it reproduces is coordinates on this moduli space of flat connections that are very well known. So these are the so-called Fock-Goncharov coordinates. And moreover, if you now do the same thing across the flip, so suppose that you flip this network, you find the network corresponding to the dual triangulation, and you do the same computation. You get an expression like this as well, but now, of course, all these nks, ls, and m's, they will be shuffled. But they will be shuffled in such a way that if you relate the 2 computations, and you have to do this not only for gamma, but also for this dual cycle, you'll find exactly these identities that we wrote down last time. And so these identities are known as KS, Kontsevich-Soibelman symplectomorphisms. So why are they called symplectomorphisms? Because these coordinates that we are constructing so in the end, these x's, they were sets of coordinates on this moduli space of flat connections on C, and they have a special structure, namely their symplectic coordinates, so they're darboux. So the x, gamma w are darboux coordinates. So what that means is that the symplectic form, holomorphic symplectic form on this moduli space of flat connections, I can write it in the form, well, let me take maybe a larger lattice. So suppose I have a generic lattice, then it would have this form, gamma I, over x gamma I, wedge d of x gamma. So this is a bit of a funny notation. So let me explain that. So they're darboux with respect to a choice of A and B cycles on sigma. So these gamma I A, gamma I B, they're a choice of A and B cycles on sigma. Right, so I've shown you sort of how these spectral coordinates, how they can be obtained in principle from spectral networks. They're the darboux coordinates. We have also now seen how this might give rise to this Kontsevich-Soibelman symplectomorphism. So this is symplectomorphic because it leaves that symplectic structure invariant. And so this is going to lead me to, well, something that I should say now as well, to the wall crossing formula. And so that's that's a result from the first of the famous series of papers by Gayotto Moore-Neitzke, which says that, well, right, what does this wall crossing formula tell me? So suppose now that I'm on the Coulomb branch, and I've got a wall of marginal stability I know that the spectrum of BPS states is going to change if I cross that wall of marginal stability on my Coulomb branch. So we looked at an example of such a wall. So suppose that I'm in the Seiberg-Witten theory. Then on one side, I could be in the strongly coupled region. And the plane of central charges, so the central charge plane, will look something like this. So I have this monopole and the Dian vector. And as well as their anti-particles. And on the recoupling side, we saw from just the theory of spectral networks that you have a quite different structure. Namely, you have this infinite set of states. In particular, there's the W boson, whose phase is an accumulation array. So there's a limiting set of BPS rays. And then there is the anti-particle stuff as well, where now the monopole and the Dian have exchanged places. And so one thing that we can write down is a product So suppose we're considering our spectral networks. Suppose we take some half plane in the spectral charge plane, and suppose we're going to look at the spectral networks at each of these phases, and we register it when the topology of this spectral network is going to change. So we get on this side a product over BPS rays. And in this case, that's just 2 rays. So we're going to denote this as follows. So okay, so to each of these BPS rates, I'm going to associate one of these KS, these Kontsevich-Soibelman symplectomorphisms, which will be labeled by gamma as well as by the phase. And these mappings, they don't commute, so I have to choose an order, and the order that I'm going to choose is, well, I'm going to change the phase from 0 to 2 pi, and then I'm going to denote all these KS symplectomorphisms in the way that I encounter them. So in this case, it will just be a product of 2 of them. It will just be the one corresponding to the monopole and the one corresponding to, this is gamma monopole, and the one corresponding to the dion. But if I do this on the other side, obviously I get an infinite product. Right. So these transformations, they were symplectomorphisms. They left this symplectic structure invariant. So since we don't want to have any singularities on our physical moduli spaces, especially not if they're coming from string theory, because strings naively evade these kind of singularities, we want that the metric is a continuous object. And one thing that is needed, or one thing, well, okay, so if this product on this side would be equal to the product on the other side, then that is a sequel of this equality. So this is the Giotto-Neitschke argument that these wall-crossing formulas, they can be explained in terms of 4-dimensional n equals 2 theories as the fact that you require, or the metric on this moduli space, which is really the moduli space, yeah, on this moduli space needs to be smooth. Okay, so I quickly wanted to say that. It's not maybe the main point of. Are there any questions? Yeah. So I'm going to argue that these coordinates, these axes, that they have a direct physical interpretation. These transformations, they will have an interpretation as well. They will then correspond to, yeah, basically, okay. So what I'm going to do is I'm going to define a new generalized partition function from these axes. And because of these transformations that these axes satisfy, that partition function is encoding the 4D BPS spectrum in a natural way. So that's how it's going to be related. Any other questions? I realize this is a bit heavy, But yeah, so the point to take away is that these coordinates that we can define from spectral networks, that they are really sort of canonical objects that we might want to look at. And in particular, that they're transformations across BPS rays, that they encode this information of the BPS index. Right. Okay. So to make a, okay, right. So how shall I do this? Yeah, let me start out by actually introducing that partition function, and let me then go to a simpler setup where I can explain this, and in particular the relation to exact WKB, as that was the main topic of this lecture. Right. Before I do that, I want to say one thing, which is going to come up later. So these coordinates x gamma, they're local coordinates on M flat. And so for some of you that might have seen a little bit about Hitchin moduli spaces and so on, you might know that there is a special holomorphic Lagrangian submanifold. So this submanifold is sometimes called the brain of opers. And there is a lot to say about opers, but I will try to be very basic here. So how can I understand this submanifold? So whereas a generic element in M flat is a flat connection, this will be denoted by an oper connection. And so what specifies, what makes this connection an oper connection? So if I think about these connections, certainly on just a flat plane, like, or on C, say. Ah, sorry, yes. Yes, right. Yeah, it's one oper in multiple opers. So if I have a flat connection, I can represent that as a 2x2 differential equation. And so what I might try to do is I might try to write this rank 2 differential equation into a differential equation which is now of rank 1, but of degree 2. So here I'm restricting myself to k is equal to 2, but something similar happens for any k. So what is the obstacle to doing this? Well, if you want to do this, you will need a gauge transformation that basically does this in every local set on your Riemann surface C. And that gauge transformation that could get singularities. And these are known as apparent singularities in these kind of in this literature. The opers are the ones that do not have these singularities. And it turns out it's actually quite instructive to work this out for, say, the cybercritin theory, how these open flat connections, how these open connections look like. You'll find that this Lagrangian, so it's, well, we already know that it's a Lagrangian, but you'll find that it's half-dimensional by doing that computation. So let me give an example of how they look like for the cybercritin theory. So the point of, well, sort of one of the main points that I want to make here during this talk is that even though there's a lot of sort of fancy mathematics involved, you can make all of this very concrete and do actual computations with it and get actually interesting sort of physics objects. And so in particular, you can try to write down what this space of opers is in the pure SU2 theory. So remember that in this case, in this example, we had our UV curve, which was this sphere with two irregular singularities. And so what I can write down is I can write down all the differential equations, holomorphic differential equations on this sphere, which have the right kind of singularities at the punctures, but do not have any singularities elsewhere. And so that will be exactly the parameterization of this Lagrangian. So you'll find that they will have the following form, which looks very much like the cybercritin curve itself, except that there will be a new complex parameter. So remember, for the cybercritin curve itself, we had a u here. Now I have some unknown parameter u tilde. So just looking at flat differential equations with the right kind of singularities, I get this structure. These are all of them. And, well, so as a physicist, if we see a differential equation like this, we want to put an h bar here. And so this is something that I'll do as well. And I call it epsilon. And so this is going to be related to putting this SU2 theory in an omega background. To be very precise, what I'm meaning by this mathematically is then that I'm looking at epsilon opers, or epsilon connections. Right, so I've got my space of opers. And now I know that these coordinates that I've introduced for any network that I can think of, I can, well, let's say it like this, I can evaluate them on these oper connections. So we've seen sort of explicitly how these coordinates arise as holonomies of the abelianized connection. So given this connection, this oper connection, I can do the same. I can abelianize that, and I can associate, I can compute what this spectral coordinate is, and I get something very explicit. Right. So this is going to be the basis of this partition function that I introduced. And I'm actually not sure, I don't know a really good name of this partition function. So I don't know, I just call it new for the partition function. And in a sense, this is going to so it's going to quantize my cyberquitting theory that cyberquitting geometry that I had. So maybe I should call it a quantum cyberquitting partition function or something like this. Remember that, so in the classical world, semi-classical, well, of course, cyberquitting geometry is quantum as well, but it's quantum now with respect to this epsilon. So what we had previously in the cyberquitting geometry was this Coulomb branch, and then we had this SP, well, in general, 2n, z bundle over this Coulomb branch, and we had this holomorphic section, df, dA, dA, df, dA, and A. That's what I'm going to come to. Yeah, yes. Thank you, yes. Let me first define it and then make that relation. So instead of that, what I have now is I have a Coulomb branch, and I have my plane of central charges, right? So my spectral network was indexed by a vacuum as well as an angle theta. And over this space, I now have another bundle, another SP2n, z bundle, but now it's it has sections given by my coordinates, gamma, well, A, gamma, B, maybe indexed by the point at which I am. And so these coordinates, they have this nice structure that, so this Coulomb branch, think of it as a space which is divided into regions by these walls of marginal stability. And so in each region, outside of such a wall of marginal stability, nothing will happen to these axes, at least if I leave the phase theta the same. But then I also have my phase plane, my central charge plane, with all these vectors labeled by the BPS charges. So I know that my objects, when I cross theta, they're going to jump if I cross one of these BPS rays. And so where the cyberquitting geometry was characterized in terms of this pre-potential, I'm going to do a very similar thing. I'm going to define some new object by saying that, and this is something that I will make a little bit more specific later. I'm going to say that I now just define these spectral coordinates for my A cycles to be equal to A. And then I'm introducing a new object. And I have so this is, sorry, there needs to be the log-run of this. And there's some proportionality constants as well that I'm ignoring. So there will be this new object, so now I have the problem, I don't know which name, so maybe df BPS, because it's going to encode the BPS spectrum, and so it will depend on A, and it will depend on epsilon. Right. And I'm claiming that this is a generalization of the cyberquitting prepotential, and moreover, it's a generalization of the Nekrasov instant-on partition function. And to convince you of this, I need to show the relation to exact WKB. But let me first answer Sergei's question. How is this object going to be related to the Nekrasov partition function, and let me do this in the NS limit, because I've mainly talked about the NS limit in detail here. I've only have one epsilon. So the relation is going to be as follows. So remember that this spectral network, which depends on the vacuum as well as the phase theta, it generically had this form of a triangulation, but we also saw that there was a special, very special geometry topology that the spectral network had at this accumulation rate, at the phase corresponding to the W boson. So maybe for Sergei, who didn't see this previous time, and so this is going to be my UV curve. So it has two singularities and also branch points at these singularities, as Francesco mentioned. And so the network at this phase, so we saw last lecture that it has this special topology which has a ring domain of compact cycles. So it's this topology which is going to show me that this BPS state is actually of a spin 1 BPS state. So, of course, it's a very natural question then. To ask, what are these objects that I get for such a spectral network? Notice that I only have this spectral network in the weakly coupled region of the Coulomb branch. I don't have such a network in the strongly coupled region because I don't have any W bosons there. So this is only there in the weakly coupled region. But I can still compute these coordinates as coordinates, local coordinates, on the whole moduli space of complex connections, complexified connections. And what I find is that for a phase which is equal to such a Fenchel-Nielsen phase for, sorry, I'm already giving it away. So the W boson, phase corresponding to the W boson, I find that these coordinates, they will be complex Fenchel-Nielsen coordinates. But not only that, I now have a very precise way of actually computing what these spectral coordinates are. In particular, I can compute them so I can compute them using my abelianization in sort of the analogous way that I did this for these networks, these generic networks. And so in this case, let me just write down the formula to be specific. So what I find in this case, well, maybe actually in the, well, it's not very, okay, let me write it down. It's not, maybe not very illuminating, but just to show you sort of what kind of expressions you get. Again, you get some cross ratio of sections. But now I have to explain you what these sections are in this case. So remember that these sections in the generic case, they came from a choice of framing. And so in this case, for one of these Fenchel-Nielsen networks, as I call them, you also need to choose some framing. And at the punctures, that will be similar to what we did previously. So we again choose some sections, S1 in this case, S1 to be part of some line bundle that is invariant under this flat connection. And so we do the same here. We also choose this invariant section, and maybe actually, for clarity, let me leave out. Sorry, and this is actually prime. So that's how these sections S and S prime in this formula come about. For a Ventral-Nielsen network, I need to do something else. Namely, I have a basis here, and I need to choose basically the ordering of that basis. But these S1 double prime and S2 double prime, they will correspond to the abelianized flat connection in this ring domain. Right, so what I'm saying here is that for any flat connection, I can compute what these coordinates are in terms of a certain choice of basis of these flat connections, of sections of my flat connections. Right, yeah. Oh, yeah, yes, right. Yes, thank you. Yes, this one needs to be done. Yeah, there are lots of cancellations, but I won't write down all the cancellations here. So, right, so it's a very, very simple formula as well in terms of these sections. It's almost like a cross ratio, but it's a different kind of coordinate. And in particular, what I can do now is I can use my proposal and I can try to compute what this new generalized prepotential is. And so suppose that I can compute this for an A cycle first, and then I compute this for a B cycle. And so I could do this for any weakly coupled, in any weakly coupled region of an n equals 2 theory of class S. And I get essentially the same result. So if I set this to be equal to A, so A is now just a new sort of coordinate. And again, I have to use the logs of these. And then I compute the B coordinate in terms of A, and what I find is that this is exactly the NS, the derivative of the NS prepotential. So this object, so the NS prepotential is encoded in terms of this family of objects. And the picture is even nicer. So, for instance, if I look at the wall on the column branch, so I can now compute what these objects are on the strong coupling side, as well as on the weak coupling side. So even though this NS prepotential, this NS superpotential, as it's usually called, this generalized prepotential, that is only defined, at least from physics, for Lagrangian theories. So that means in these weakly coupled regimes. But now we can do this in any regime of any theory of class S. And so we find an object that is going to jump across all of these BPS rays. So here it has kind of a complicated structure. because there are many jumps. And so remember that the phase here was the W boson phase. That was this accumulation ray. But I could also compute what these spectral coordinates are. So I could also compute this in this, say in this region. Maybe I call this theta opposite. And right, so this is where my sort of question in Sergei's talk came from. So if I compute it there, I find a relation with what is sometimes called spectral determinants or non-perturbative partition functions as were computed by people like Marino, Grassi, etc. So whereas here I get this relation to like physics in omega background. The opposite phase, I find some other connections. And I don't have any time to talk about that right now, but this is something that I could explain here if you're interested. And so I think in some sense this new partition function is sort of encoding any sort of interesting object that we know about in this context. I think it also encodes the isomonodic time function, although that is still a computation that I need to do. Sorry, that was. Yeah, yes, that's right. Yeah, so I didn't say that very explicitly here, actually, but so here I computed these on this locus of Opers. And that's how I got the relation to the NS free energy. But I could do this for a general Oper, and I think there's a relation to the isomonodic tau function then. Yeah, so if anyone wants to help me with that computation, then I would be very grateful. Right. So for the main thing that I wanted to do in this lecture, I only have 10 minutes. So let me just give a very brief sort of indication of that. So you might wonder, how come that these spectral coordinates, how come that they're so close to this prepotential? And so this is going to be because of a relation between abelianization and something that is called the exact WKB method. And so I don't want to talk about this in full generality, but I want to look at a simpler example to show this relation. So basically, I want to consider two-dimensional theories here. So if I have any two-dimensional n equals 2,2 theory, then I know that such a theory has a space of a modular space. A space of deformations. And because of the structure of 2,2 supersymmetry, I also know that the vectra of these 2,2 theories, they form a covering over, so a covering inside of the cotangent bundle of that moduli space. Now there is one example of n equals 2,2 theories that appear inside of the four-dimensional ones. Namely, I can look at certain defects, surface defects that Sergei knows everything about in these four-dimensional theories. And I can look at a specific kind of surface defects that are called canonical surface defects. I don't have time to explain exactly what that is. But the main point here is that their moduli space is exactly this UV curve C, and the covering is exactly the Seiberg-Witten curve. So I'm going to look at two-dimensional theories now. And these two-dimensional theories, their moduli space is equal to C, so that means that if I choose a point Z on this moduli space, that characterizes one particular two-dimensional theory. And that one particular two-dimensional theory, I'm looking at massive ones, they have a finite set of vacua, and the vacua are exactly given by the fibers, by the pullbacks to the fiber. And let me denote that like this. So I have this really nice geometry of vacua which are fibered over this moduli space. So we talked about spectral networks, and we saw how four-dimensional BPS states are encoded in terms of these. But it actually turns out that two-dimensional BPS states, which are coupled to such a surface defect in the four-dimensional theory, they're also encoded in the spectral networks. And so how come? So this is because we need to think of such BPS states as tunneling, some quantum mechanical tunneling between these vacua. So this is going to correspond to one cycles, but now open one cycles, which go from the vacuum I to the vacuum J. So instead of being closed one cycles on sigma, we now have open one cycles that characterize these BPS states. So this is going to be the electromagnetic charge of my BPS state. And in order for this to be BPS, well, so I said it's BPS, but for a generic open path, this will not be BPS. It will only be BPS if we satisfy the BPS condition. So that is, if the absolute value of the central charge of this BPS state is equal to its volume. Up to some phase. And this phase is now the two-dimensional, the phase of the two-dimensional BPS state. Sorry, this is an equation that doesn't make any sense. Like this. And that was exactly the condition for spectral networks, right? That was exactly how we found the trajectories of the spectral network. Except that now we're looking at a different kind of cycles. We're looking at open cycles. So let's look at an example. So suppose that we have a generic network. Well, actually, let's just look at the neighborhood of a single branch point. That will be enough for us at the minute. So our network will look something like this. We're considering a particular surface defect in the theory, a particular two-dimensional theory, coupled to the four-dimensional theory, and that will be labeled by some parameter C on C. So this network was drawn for some phase theta. Well, now I can look what happens if I change that phase theta. And what is going to happen is that this network is going to rotate. And so if I rotate this network far enough, then what is going to happen is that it's going to hit this point Z. So I'm leaving my point Z the same, but now my network is going to hit the point Z. And this is a special phase, and I call this quite indicatively the two-dimensional BPS phase, because what is happening at this phase? At this phase, there is exactly this cycle on the covering, so this, well, or maybe I should use blue. This blue is happening on the cover, so I start out on the ice vacuum, and I go to the J's vacuum. So blue is from Ci to Cj, so this is happening on the covering. And because there is a trajectory here, I know that that lift of the trajectory, that's going to be a BPS trajectory. It's going to satisfy the BPS constraint. So this is how I find the two-dimensional BPS states in my theory TZ. So this is my two-dimensional theory living on that surface defect. Right. The next step and I'm not going to be able to tell you all details, but hopefully Sergey will fill in some gaps about Borel summing later today. Right, so we had, okay, so we were looking at a particular two-dimensional theory, well, surface defect, let's see. T to the C inside of our 4D n equals 2 theory. And for these surface defects, there is a way that we know how to compute partition functions for them. So these are called vortex partition functions, and Sergey and I know everything about those. And these partition functions, they satisfy a differential equation. And that differential equation is exactly the differential equation that we saw before as the Oper equation. So these have partition functions. Say C2 vortex. And they obey the Oper equation. So that is, they obey some degree k differential equation, which depends on this epsilon. I just write it down schematically like this. Well, sorry, not like this. So this is a differential operator which looks like epsilon squared dz squared plus some other terms. Right. Well, this is actually a setup that mathematicians know and have studied very well. It's the setup of of exact WKB. So let me see, how can I do this in 5 minutes? Yeah, let me do this in terms of this picture, perhaps. So if I have a second-order differential equation, then we know that it has a basis of solutions, a two-dimensional basis, or k-dimensional in general. But there is another way that I can try to construct solutions. So now I'm going to write down my z as a solution psi. So I can construct solutions to my differential equation. I can also do that asymptotically in epsilon. If my differential equation is kind of too hard, or just if I'm curious about this, I can compute solutions asymptotically in epsilon. So this is called the WKB method. And as a first approximation, you'll find that these solutions, they'll go like e to the power 1 over epsilon times the integral of the one form lambda, where the one form is the Seiberg-Witten one form of the corresponding four-dimensional theory. And then it has obviously epsilon corrections. In particular, if I look at monodermies of the solution psi, they will go like periods of lambda. And periods of lambda, we know what they are. They are related to the prepotential. So this is going to be the relation to the prepotential. But the story is nicer. So so let's go back to this picture. So suppose, for instance, that we consider a differential equation, a very simple one, so the Airy differential equation. Which is given by w squared is equal to z. If I look at its solutions, so its solutions, well, oh, sorry, this is the curve. This is the differential equation. Well, let's do this a bit more careful. Right. So if I look at its solutions, I'll see that the solutions, there is an asymptotically growing and asymptotically decaying solution. And, right, so they will go, let me combine them. They will go like e to the power plus or minus 2c to the power 3/2 over 3 epsilon. So I can wonder, where do these solutions decay the fastest? So I can draw on my plane. So I can draw on, so this is all defined on the surface C is equal to just a complex plane with my variable z. And so there is a corresponding spectral curve, which is the one that I wrote down before. So this is my sigma. So I've got a sigma, I've got a c, and I've got an OPER equation. And so this sigma has a branch point at c is equal to 0. And I can work out sort of where my solutions will grow and decay the fastest. And that will depend on the phase of this epsilon. So I might find something like this. The point is, because of this factor c to the power 3/2, there will be 3 of these trajectories coming out of the branch point. So this might look familiar. And if you look at the relation between this, and you try to do this in general, you'll see that these Stokes lines are exactly giving you a spectral network. Now, so what exact WKB method tells you is that you can not only do this asymptotically in terms of epsilon, but you can even do this analytically in terms of epsilon. And so what exact WKB method does is it constructs analytic solutions in epsilon using Borel summation. So this is something that I can explain to you later if Sirke doesn't do that, because I think it's important in his talks as well. The point is, okay, so this is basically the canonical way in this setup to turn an asymptotic series into an analytic series. And so suppose that I do this, and I draw my point Z here because of space issues. So I can take the Borel sum with respect to a certain phase. I can do that with the plus solution, and I can do that with the minus solution. And now I get solutions which will be analytic in epsilon, as well as obviously in Z. But they depend on the phase theta. So what happens, what turns out to happen is that this phase theta is exactly correlated with this phase of the spectral network. So if I change this theta here, so this Borel sum depends on a phase, the phase correlates with the phase of the network, and what happens, so is that these solutions, they will be locally constant at theta, in the sense that it's okay if there's no walls crossing this particular point. But then if I'm at the phase where this network has rotated, and where one of the walls, one of the trajectories hits the point C, there's going to be a jump in this Borel transform. And that jump can be computed exactly, so it can be computed, well, let me see. Yeah, so it can be computed in something which is called a Lefschetz symbol in the theory of exact WKB. And it basically corresponds to looking at this, at the lift of this trajectory to the covering, starting at some vacuum I and going to some vacuum J. And so the change in this Borel sum is going to be exactly proportional to this factor. And that factor is exactly the central charge of this two-dimensional BPS particle. So this is how we give an interpretation of exact WKB in terms of the two-dimensional theory living on the surface defect, because it produces these solutions which exactly encode the two-dimensional BPS states, whereas at some other phase, they correspond to this two-dimensional vortex partition function. So the story, the lift of this to 4 dimensions is very similar, in the sense that what you can now do, instead of looking at open paths, you can look at closed paths. So you can look at the monodromy of these solutions around loops, around cycles, one cycles, on your cybercritic curve. And so in that case, in the world of exact WKB, this is called the Varro period. I'll just mention the name. And it turns out that the relation between exact WKB and abelianization is given by the following observation. So this Varro period is exactly the spectral coordinate of the, so this Varro period also depends on your theta. This depends on theta, and it's equal to the spectral coordinate evaluated at this differential equation that you started with. Right. So that tells you then that these spectral coordinates, that they have these nice WKB properties because our solutions, psi, they had this WKB approximation in terms of 1 over epsilon. Yeah, so basically this is how it's going to lift to 4 dimensions. And that's where I need to stop. So sorry if that might have been a bit technical, but again, yeah, so please ask me any questions. That's right, yeah, yes. Well, this object is much more general than this vortex partition function. It's like in the 4-dimensional setup. So you could define this general partition function, which depended on the phase. And then at a certain phase, it was equal to the Nekrasov-Shatasvili superpotential. But it's defined everywhere, for every phase. And it's like that as well here. So there is a certain phase for it which is this vortex partition function. But then it's a much more general object. So it encodes all these 2-dimensional BPS states. Mm-hmm. Yeah, so we've been working in a background R4 and computing partition functions there. If you would do it on R3 times S1, you would get the superconformal index. I have not thought about such an object in that. It's just a different setting. It's a different setting. Yes, yes. You can study your 4-dimensional theory in any background that you want. So this is specific to this Nekrasov omega background. Mm-hmm. Yeah, yes, definitely, yes. And so one of the things that we did, so most of this is like, work inspired by collaboration with Annie Neitske. And so one of the things that we did is we did this for the E6 theory, the Minahan, the Mishansky one. And so, the only thing which, so there is this dictionary between mathematics and physics. And what it boils down to in this case is that Lagrangian theories seem to correspond to nice differential equations in the sense that you know a special basis of solutions to these. Whereas the non-Lagrangian ones, for those, there is no such special set of functions. So that's some problems that you have in the non-Lagrangian theories in order to write down analytic results, but you can compute them numerically everywhere that you want them. So in that sense, we completely know sort of how they behave. We just don't know the analytic expressions, which is, Mm. Mm.